Section 3.11 is linearization. Now I copied this right out of the book. It says sometimes we can approximate complicated functions with simpler ones that give the accuracy that we want for specific applications and are easier to work with. The approximating functions discussed in this section are called linearizations, and they are based on tangent lines. Other approximating functions, such as polynomials, are discussed later on in Chapter 10. In Chapter 10 is where you're going to be using this in Cal 3, okay, with the other functions. So this comes from the point-slope formula of a line. Do you remember the point-slope formula of a line? Because it's been so long since algebra, I'm probably going to remind you. And yet, look at me, I am. The point-slope. Okay, the point-slope formula of a line is what you use when you know a point, x1, y1, and you know a slope, m. It's y minus y1 equals m times x minus x1. Do y'all remember this? Y equals mx plus, oh, that's the slope formula, general, yeah. Okay, if we solve this equation for y, we're going to end up adding this y1 right here plus m times x minus x1, right? And if I told you that our point, instead of being a point xy, what if I told you that it was a f of a? And I told you that the slope was the derivative evaluated at a. This is your point. And this is the slope. In place of y1, we would plug in f of a. You see that right here? Okay. In place of the derivative, we would plug in f prime, and in place of m, we would plug in the derivative. See that? And in place of x minus x1, we use x minus a. So this linearization formula came from the point-slope formula from Algebra 1 in high school. Maybe Algebra 2, I don't know where they teach it. Some algebra class way back in the dusty bookshelves of your brain. Okay. Not for everybody. My kids didn't take algebra in 8th grade. All right. So here's the definition. If f is differentiable at x equals a, then the approximating function is the linearization of f at a. And that means that your function is approximately equal to this linear function. So no matter how complex your function is, we can come up with a linear equation that approximates your function at that point. Now here's what I did not do. Let me go, bear with me for a minute. I'll edit this out of the video. I want to go to the PDF files here because I did not include this, and I probably should have included this graphic. All the way down here to linearization. I know what picture I'm looking for. Aha. Copy. Let's go in here. And we will paste. Aha. So, here's a quadratic function. Right here in blue, y equals x squared. And there's the linear tangent at this point. At the point 1, 1. And if you zoom in on this function nearer to the point 1, 1, what we see is the graph of this function and the tangent almost look like the same line. They're exactly the same over this region close to that point 1. So rather than work with a quadratic function, linear functions are easier to work with. Okay? So let's look at an example here. I want you to find the linearization of a cubic function at x equals 3. Okay? So we're going to go through the process. I need two things. I need the a and f of a. And I also need the derivative evaluated at a. Right? So I start with the function, and I'm going to take the derivative. The derivative is 12x squared plus 5. That's it. The derivative evaluated at 3 is 12 times 3 squared plus 5, and that is, calculators, how many? 149? $113? And the point is at 3. What is f of 3? Go into the function 4 times 3 cubed. That's 4 times 27 plus 15 minus 3. 4 times 27 plus 3 plus 15 minus 3. Okay. So the linearization then is going to be the formula L of x equals, it was the f of a plus the slope evaluated at that point times x minus 3. Right? That came from this linearization formula, f of a plus f prime of a times x minus a, which was just, we saw a twist on the point slope formula of a line. Okay? So why is this nice? Well, let's say we wanted to know what f of 3.1 is. Your question?
F of a, you said equals 120.
Mm-hmm.
And then that was F of a plugged in 3 in the function.
Uh-huh. Yeah. F of a, you plug 3 into the function. To get the slope, you plug it into the derivative. Okay? Dishan? No. Are you looking at this right there? X equals a. Yeah. A is 3. So x is 3. We don't do 3 minus 3 to get 0. That violates the order of operations. We got to do the multiple. Oh, you mean at the bottom? Oh. Right. That's the value at, no. Yeah, because if I wanted to know what f of 3 was, well, we already found out it's 120, so yeah, that's going to be 0. The linearization approximates the function. So let's look at this. If I wanted to know, let me grab a different color here. It's 4 times 3 cubed plus 5 times 3 minus 3. You plug the 3 into the function. So let me pull up the calculator because I want to do a table comparing some things here. All right. If x is equal to 3, we've already observed 3 minus 3 is 0. This is going to be 120. Sorry. And f of 3 is also 120, right? What if x is 3.1? Well, that's going to be 113 times 0.1, which is 11.3 plus 120, and that's going to give us 131.3. Is that right? But if x is equal to 3.1, what is f of 3.1? Well, I can do L of x in my head. F of x, not so much so. If you plug in the function, this is what I wanted to show you. Let me switch the view. I don't want to see all that. If we plug in the function, yikes, f of x equals 4x, to the third plus 5x, didn't take the plus, minus 3, and then I go to the, let me also plug in the linearization function we got, 120, thanks, 120 plus didn't take, 113 times x minus 3 and then we go to the table. It didn't hit the table. Second table set. Second. Yeah. I wanted to ask, so I think this is right. If x is 3, we got 120 for both. If x is 3.1, not 31. Remember the first function I put in was the function f of x. Here we get 131.66. Let's say 0.7. You know, that might be close enough for government work, and it was quick and easy. I could do it in my head even. But this one, there's no way I could do that, evaluate that function in my head. Do you see how the linearization can help you out? Let's say you want to get even more precise. How about 3.01? Well, if x is 3.01, then that's 0.01. That's 1.13. That's going to be 121.13. And let's say this is 3.01. And we get 121.13 for the function as well. But I can do the linearization function in my head. It's just a matter of moving decimals when I'm close to 3, right? But on the function, it's much harder to cube 3.01, multiply that by 4, and then add 5 times 3.01 and subtract 3. That's too hard to do in my head. But if I'm only interested in what's going on with that function close to 3, then my tolerance is within that range. Then I can use this linear equation to approximate the function. You're going to be doing some of that in differential equations as well. We use series and polynomial functions to approximate transcendental functions or trigonometric functions. So this is not going to be a foreign concept as you continue through your mathematics career. The linear function is easier to work with. There's an R there. And it can be used to approximate it can be used to approximate the function close to x equals a. Now, close I underlined because how close is close? Well, it depends on your tolerance and the problem that you're working. Okay, and that's where the differentials come in. All right, so speaking of differentials, let's let y be f of x be a differentiable function. The differential dx is an independent variable. The differential dy is dy equals the derivative of x with respect to x dx. So this kind of makes sense intuitively, because if you have dy dx equals f prime of x, isn't that, this is Leibniz notation, the dy dx? And here's another notation, f prime of x. If you multiply both sides by dx, if this were a real ratio like this is what you would end up with, right? If you multiply both sides of the equation by dx. Well, dy is just the change in with respect to y, or the change in y, as x changes by dx. So that's that wiggle room that you're talking about in the linearization problem, your margin of error there. So in this next example, I want you to find dy. Well, following what we've seen up here, dy dx, is equal to, let me rewrite this function, shall I? Y is equal to sine 11x to the 1/2 power. So dy dx is equal to what? Cosine 11 square roots of x times 11 halves x to the negative 1/2. Right? Cleaning that up, we get dy dx is equal to 11 halves, let's do it like this, 11 cosine 11 square root of x over 2 square roots of x. Y'all okay with that? And I'm not going to rationalize the denominator. So what we would come up with then for our differential is dy is equal to 11 cosine 11 square root of x over 2 square root of x dx. Okay, these are called differentials. The differentials is kind of like your margin of error.
It's the same thing, just put by dx over x.
Yep.
What do you mean by margin of error?
When we look at these graphs right here, we say as we zoom in, this blue graph is not exactly the same as the pink graph, which is the tangent line. It's that error. It's how far those graphs are apart from each other. So when we made this table right here, we saw that we were off by 4/10 between the function and the linearization approximation. Okay, that would be dy, and dx would be 0.1. Okay. All right, any other questions? Okay. Then we will stop this recording. Stop. Stop.